All right, well, welcome everyone. I am JJ. Let's just jump in and tackle an example problem. So we're taking a look at distributed loads this time. We're just going to do it on a beam. Let's determine the support reactions for our beam shown. So we have a pin at A, a roller here at C. So we can find AX, AY, and CY in here. So let's just come in and go for it. If I'm given a distributed load problem, one of my steps is going to be to say, how do I break up that distributed load? So let's say, well, I have a rectangle over 20 feet here. Let's call that area number 1. Remember, the force from a distributed load is just the area. The area of a rectangle is base, 20 times height, 27. And then I also have a triangle on the left side here. Let's call that area 2. Over here on the left. The area of a triangle is 1/2 base, 9, times height. We go up to that maximum point here, 27. So we can find the area of both of those. But to do that, we're going to need, or to do our support reactions, we'll need to apply equilibrium. For applying equilibrium, we should always have a free body diagram that goes along with that. So let's just come in and draw it really quick. So I have my beam as a horizontal line going all the way out to the far right edge of this. At A, I have a pin. So let's put in an AY and an AX. AY and AX. Just guessing directions for them at this point. At C, I have a roller. Roller should have one force perpendicular to whatever they're rolling on. If the ground is horizontal, then we have a Y force. And then we'll just show our distributed load along the top of this. It goes for 9 feet, which gets us to about here. And then we can come down with that. And the rest goes horizontal across the top. We'll just put a handful of arrows coming down off of these two distributed loads in here. Something kind of like that. The first section, that triangle, we know is 9 feet wide, 9 feet. The next section from B to C is 20 feet. 20 feet. So we can get all of those labeled in there. I also know that maximum height here, the maximum height of the triangle, or the height of the entire rectangle is W equals 27 pounds per foot. So in that rectangular portion, every foot that we go in adds another 27 pounds of force on here. In the triangular portion, we're linearly increasing from 0 up to 27. We can work with that. 3 unknowns, I can find all of them. Even without knowing what to do with my distributed load, I should be able to come in and get my AX for this. There's no forces in the X direction. My distributed load is going straight down. So I should be able to come in and start here and say, summing forces in the X direction, all that I have is AX. There's nothing else in the X direction, so this has to be equal to 0, which means AX equals 0 is going to be my first of my 3 answers. The other 2, though, I'll have to deal with that distributed load. If these are just individual forces in here, we would just say, well, I could sum moments up at A. We probably all can tackle that. Summing moments at A, I'd eliminate AX and AY. CY would be my only unknown in the equation. We're still just going to approach it that way. With positive going counterclockwise, let's sum up our moments about point A. About point A. Remember, moment is force times distance for us. The force for a distributed load is the area of it. Let's actually write that down. The force of a distributed load is its area. So if I'm summing forces, I just include the area in there. If I'm doing moments, though, I need area times a distance again. It feels like we're sticking another distance in because we need one distance as area. One will be for where the moment is. So let's come in and get this. Again, I split this into 2 areas. Let's just do those in order. So for area 1, I would say my moment. All of my arrows point down here. If I point down, I would spin clockwise around A. So I'd have negative, because it'd be a clockwise rotation. I took counterclockwise as positive. Force, so I need my area of this in there. The area is base times height, 20 times height, 27, times, I need my distance from A 2 for the rectangle, we want to get to the very middle of the distributed load. So from A to the middle of the rectangle, I'll say I need to go 9 to get to the beginning of the rectangle. From the beginning of the rectangle, I go half the width of the rectangle, plus 20 over 2. That first 9 gets me from A to the beginning. That second 20 over 2 gets me from the beginning of the rectangle to the middle of the rectangle. But our two pieces in here are really, this first one was just what's my force. Force from area 1, so F1. That second one was my distance from A to the midpoint of my rectangle. That'd be one of them. Let's get that triangle in there then. 2 would also be causing all of my arrows would be a clockwise rotation, so minus the area of a triangle is 1/2 base times height, so minus 1/2. The base is 9, and the height is 27. 9 times 27. And then I need, what's my distance on this one? Distance for a triangle should always be 1/3 of the way into it, measuring from the 90-degree angle. Or we could say 2/3 from the pointy side of our triangle. I pretty much always do the 90-degree angle because then I'm remembering one rule, which sets me up to be more successful. But there'd be nothing wrong with doing 2/3 of 9. But I would write this as, I need to get to the 90-degree angle from A, so 9. And then I backtrack 1/3 of the way in to about right here. 9 minus 9/3. Again, that's the exact same as 2/3 of 9. It's just, how do we approach that? What makes sense for us? Either way, it gets us the same thing. Those first 3, 1/2, 9 times 27, that's my area of shape 2, the triangle, which becomes just the force. This is my force for shape 2, F2. And this piece right here, that's my distance. Distance to area 2. Again, for a rectangle, we go to the very center of it. For a triangle, we go 1/3 of the way in from the 90-degree corner. And my last piece in here is CY. CY would cause a counterclockwise rotation about A, so I'll add this in. Plus, my distance is 9 plus 20, 29. My force is CY. Should get me to 0. CY is my only unknown in that. If I solve this for CY, I'm going to get here that CY is 378.93 pounds, and we're going up. I get a positive number out from this equation, so I guess the right direction for CY. Once I have CY, now I'm down to only one unknown, the Y direction. I could sum moments about literally any point I want to with AX and CY known, as long as AY didn't pass through it. Or I could just sum forces in the Y. Let's do forces in the Y. It's a little bit easier for us. So summing forces in the Y direction. I have AY going straight up. I have CY going up, but I just found CY was 378.93. So plus CY, 378.93. Minus each force. So force 1, the area from our distributed load, would be minus 20 times 27. Again, that is F1. We're not multiplying by distance again here because we're not doing moments. It's just force. Force times distance gets us moment. But then minus the area of our force 2, of the triangular distributed load. So minus 1/2. Our base is 9. And that height, we get up to 27. Times 27. Should get us to 0. Or that second area that we just wrote out here, that's the area of distributed load 2. This is F2. Still just doing the area for us. But I have only AY as an unknown because I'd already found CY in here. If I solve for AY, I would get that AY is 282.57 pounds. 0.57 pounds. And we're going straight up with that, which should be our second answer. I know it's going up because I get a positive number out from my forces in the Y equation, which means I guessed the right direction back in my free body diagram. Again, just split distributed loads into area. If we need distances, we need to know which distance we're getting to. The middle of the rectangle, the 90-degree corner in a triangle, or a third of the way from the 90-degree angle in the triangle. For statics, that's really only the two distributed loads we'd use. We can make more complex ones, which we'll see in other videos. We can kind of just reduce that down to rectangles and triangles every single time. Make sure we can work with those. We can get you there. If it's a struggle, stick around, watch more videos. Let's get you an A with JJ.